Splish splash, oh, are we starting? Sorry, everyone. Hi, welcome. Today we are going to be talking about the diminishing resources and deteriorating environmental conditions on our planet. This is the fourth part in our little mini series. Today we're going to be focusing on fresh water. This is going to be a continuation from the much larger paper that all of this is based on. You can see on screens about global warming, climate change, and environmental pollution by the following authors: Sarah Zandalinas, Felix Versicci, and Ron Mittler. I'm so sorry that I have mispronounced those. But without that, let's get on and talk about water and fresh water and why it's so important. From land, we jump back and make a splash to the seas. Water, more specifically freshwater, is arguably the most important resource that we have on Earth, as every living creature depends on it in order to grow. On top of survival, humans have found numerous ways to consume and extract fresh water, the scope of which is too large for this video. Similar to this carbon cycle, Earth has a global system for the flow of water called the water cycle, which is also greatly affected by human activity. And we can kind of see that here in this figure. So starting in the atmosphere, water is held. At a certain point, it precipitates. It can precipitate either in the form of snow or water. From there, water finds its way to the ocean, where the majority of it is stored. While there or on its journey to the ocean, it can be used in living things, including humans, or evaporated directly back into the atmosphere. That, in a nutshell, is the water cycle. And similar to the carbon cycle, there are places within the water cycle where large amounts of water is stored. Think of the groundwater, the oceans, and as we can see in this figure, this is showing all the water on Earth and where that's located. We can see that roughly 97% of all water is some sort of salt water. That leaves only 2.5% of water to be considered fresh water. Of that 2.5%, 68.7% is frozen in the form of glaciers and ice caps. Another 30% of fresh water is in groundwater. That leaves only 1.2% of 2.5% to be water on the surface or in some other form. Of that 1.2%, another 69% of that water is frozen in either ground ice or permafrost, which means the remaining percentages of fresh water are more of what you and I probably know of more than these other forms, besides maybe oceans. And that is lakes, taking up the majority of which, then soil moisture, which we don't really necessarily see, then there's water in the atmosphere, then there's swamps and marshes, and then there's rivers that we all know, and then the rest of the remaining water is in living things. So it's extremely important on how we use our fresh water, seeing as we really don't have that much. And for the vast majority of human history, the natural flow and relatively quick abundance of the water cycle allowed it to be deemed as a natural resource. Some key examples are solar, wind, geothermal, and the air we breathe. Along with that, in the same vein, there are places or reservoirs within the freshwater cycle that are also deemed to be renewable, such as lakes, rivers, and groundwater. And these are also, along with other not renewable resources, and the water cycle in general, are greatly affected by human activity. And these renewable freshwater reservoirs are the backbone to all land, organisms, and environments. But within the last century, due to over-extraction, inefficient use, pollution, etc., these three resources and a few freshwater resources have drifted into the non-renewable resource category, which is a resource that has a fixed quantity on Earth and or cannot be replenished fast enough to meet consumption demands. Some examples are minerals, land, and fossil fuels. Like we recently just said, groundwater, freshwater, timber, food, and biomass are now leading and sliding towards the non-renewable resource category. To put some consumption into perspective, Let's look at this graph here, figure 1D from the paper. It is showing again across time the amount of global freshwater use and the renewable freshwater resources. Again, we're seeing another inverse relationship here. And this data stops around 2014. I just want to put that into perspective, how much society has advanced since then. In 2014, that's when iPhone 6 came out. That's also just shy of 1 year when the global population hit 7 billion people as of 2025. The global population is 8.23 billion people on Earth, all of which, by the way, need and depend on fresh water to survive. This is also a decade before AI was widely available and used by global companies. So just like every other resource, it is vital how we use and build structures to use resources sustainably. And that means specifically building structures to meet the needs of the present without compromising the ability of future generations to meet their own needs. Sustainability is a current global challenge humans face if we want to continue calling Earth our home. Before AI, the largest sector extracting fresh water was agriculture at about 70%. Currently, AI extracts more water and is expected to use more resources, including electricity, over the next couple of decades. Which, by the way, AI is a computer system with human-esque-like intelligence with the ability to perform complex tasks such as reasoning, decision-making, problem-solving, perception, language understanding, and a lot more. AI requires large amounts of resources to function, specifically fresh water and electricity, which current numbers are best estimates based on indirect energy and water uses, as the specifics are not released to us and are hidden by these companies. In this picture here, we can see global projected water withdrawals for AI through 2027. AI alone will consume between 4.2 and 6.6 billion cubic meters of water. That is equivalent to 4 to 6 times the annual withdrawal of the entire country of Denmark. At the same time, AI is also projected to use 370 terawatt hours of energy. This is equivalent to 44 nuclear reactors running 365 days a year. This most likely a vast underestimation, as all current AI projects from the government are not included in these estimates, and our increased dependence on AI are only going to make these go up. We are going to run out of fresh water to use, and unfortunately, the current administration of the US in December of 2025 has prohibited the regulation of AI in any state. I cannot express to you how much AI needs to be regulated. The fact that it is illegal to regulate in all 50 states is a dire warning and exponentially increase environmental disasters across the globe. So where is all that water going? In short, it's mainly used for electricity. The majority of water is used for electricity, and also to cool the servers and computer parts, where indirect usage for electricity is considered scope 2 water, and water used to cool the data servers is direct and known as scope 1 water. Due to the complexity and intense computing, the components can overheat, and if they are at high temps for too long, they start to not function properly and eventually break. Specifically, these components are the central processing unit and the graphical processing unit, or CPU and GPU, respectively. The CPU is the key part of the computer responsible for interpreting and executing instructions from software and hardware, acting like the brain or control center for the computer. Whereas the GPU is responsible for rendering and processing images and videos to be displayed. It acts like the visual system for the computer. Before AI was used in these data centers, air conditioning alone was enough to cool the servers from overheating. Now, because of how intense these operations are, specifically on the CPU and the GPU, air conditioning alone is not enough to cool these racks fast enough to keep up with these demands. A cold plate has been added over these thermal components to exchange heat through fresh water. And we can see in this figure here, this is the general idea of how Scope 1 water is used in an AI data center. So a cold plate is added over each GPU and CPU. There can be a CPU here, GPU here, CPU here, GPU. You get the idea. There can be, 10 to 20 on one of these racks each, and then there's rows of racks, then hundreds of racks in the server room, and there's like multiple stories. You can see how this gets exponential. And of course, it also needs electricity for all of this to run. Okay, so water then is piped in through these cold plates. It takes the heat, it goes in as cold water, and it leaves as hot water, and goes into this hot water system. Cold water is also pumped into the AC units to blast cold air out, leaving hot air, going to the hot air exchange. Hot air exchange, hot water goes outside of the system, outside, where it goes to a cooling tower. The cooling tower allows the water to evaporate as steam and introduce more cool water, the remaining water that doesn't evaporate as steam, to go back to a chiller to keep it cold and restart this process over again. And that, in essence, is where water is being used for Scope 1 water. I need to say, in this model here, 80% of the water in this system is evaporated straight up. There's not even a turbine here for the steam to generate electricity. Although I think Scope 2 water is a bigger problem, we simply just don't have enough time to get into it in this video. We will be focusing on Scope 1 water instead. One way to use less water in the data center is to use what is known as non-conductive cooling liquids. These liquids are unable to carry an electrical current through themselves, such as mineral oil, and they're used to cool electronic devices. So in this diagram here, we can see instead of having all the servers aligned on a rack and then having cold plates on over each one of these components, the server or the computer themselves are placed within this liquid. And I know that's going to break some of your brains. How can you place electronics in a liquid and for it to still work? Trust me, it does. It's because it cannot carry an electrical charge. So it's able to function properly. It functions as if it were air. The only difference is that the heat now is going to be directly transferred into this non-conductive cooling liquid. Some water is still going to be used for heat exchange to make hot water cold, but it's going to be significantly less than this entire system. I just want to leave you with this question. Who does the water belong to, if anyone at all? How do you guys feel about AI and data centers? Let me know in the comments. But that's it for this section. Thank you so much for watching. Hope you guys have a great day and know that I love every single one of you. And here are my sources.